Okay, good morning. A little sneak peek into the world of mechanisms. We've been talking about what mechanisms look like and how to make predictions about them. We are going to be covering a lot of reactions this semester. We are not going to be testing on all of the mechanisms. There are classes I've seen, anytime a reaction is shown, that mechanism is fair game. But I am of the belief that some mechanisms make sense. They follow patterns, they follow intuition, they help you develop a good intuition. Some mechanisms are not intuitive at all. They don't make sense. It's not something you'd predict would happen. It's something you'd have to just brute memorize. So I do not require you guys to show every mechanism for every reaction that we learn. Instead, I select which mechanisms I require you guys to be tested on, which mechanisms I want you to learn. So I narrow down which ones you're going to be tested on. And I do that for Alkene too as well. And what I say in my classes is if you can master the mechanisms I've asked you to master, you can make sense of any other mechanism that you see. But if you can't master these mechanisms, you are going to struggle with any mechanism. So why make it harder on myself about figuring out which mechanism to test on this time and how hard it's going to be to grade them, because inevitably challenging mechanisms are challenging to grade because students struggle on them, and that just makes it hard to actually put a grade to it. I narrow down which ones I'm ever going to test on, because if you can master these, you can master any. And I want you guys to notice how much acid-base chemistry goes on here. First step, acid-base. Second step, Lewis-base. Third step, acid-base. Fourth step, acid-base. Fifth step, Lewis-base. Sixth step, acid-base. Here's a different version of an acid-base. It's all acid-base chemistry. I just saw a meme recently on Instagram too. It's those two astronauts standing on the moon, and one is standing in front of the other looking at the Earth going, wait, it's all acid-base chemistry? And the other one's like, it has been the whole time. Always has been. So nerdy. It's all acid-base chemistry. It's all acid-base chemistry. All right. We're going to finish up that worksheet that we were on, practicing our mechanisms. You all had a copy? You want one? Need one? Jacob, do you need one as well? Was it given out yesterday? Yes, it was. Okay, unfortunately, yours is one-sided. 2 sheets. You're welcome. You get mine. And pink. Yeah, that's the least of your... That's the least of the troubles, though. All right. We're going to go through the mechanisms at the bottom of the front side. The back side is radicals and resonance. The front side, we hadn't finished it, had we?
Yeah, we just haven't finished the resonance. We did everything else.
Now I need to look at one. Can I borrow yours quick? Thank you. You guys did it, but I don't think I put the answers up on the board. So let me put the answers up on the front of on the board, since we haven't actually gone through them together. Or I could actually have you guys try to speak them out and tell me what needs to happen at each step. In the first mechanism, the one-step mechanism, what needs to happen?
The bromine bond needs to break.
Bromine bond needs to break.
And then the carbon to nitrogen, those electrons will go to the carbon. That on the BR bond.
Good. The nitride, or sorry, cyanide. The cyanide attacks the carbon. Cn minus. Thank you.
But you know what it is. Yeah.
I heard
Yes, it smells like almonds. And if you smell or taste almonds, it's too late. Cyanide actually has a lone pair on both carbons, both atoms, excuse me. There's a lone pair on nitrogen, there's a lone pair on carbon. Can we make a prediction about whether carbon uses the lone pair to attack or whether nitrogen uses the lone pair to attack? Nitrogen uses the lone pair to attack? So it should be a nitrogen-carbon bond forming. Would it make more sense for carbon, who is less electronegative, to share its lone pair, or for nitrogen, who is more electronegative, to share its lone pair? Less electronegative, more willing to share electrons. So it should be carbon that's sharing electrons, which is why we connect it as Cn. Okay, carbon attacks, CBr bond breaks to bromine. Great. I didn't give you that Br minus, but that is a byproduct. Now you guys had worked through this pretty well. A lot of you caught on early that the chlorine-chlorine bond breaks to one of the chlorines. That's how we form the chloride. You also caught on pretty early that the pi bond attacks the chlorine, the other chlorine. This is where a lot of you got stuck. How do I make that other bond? And my encouragement to you was look at the lone pairs. If you're not keeping track of the lone pairs, it is easy to get stuck. So looking at the lone pairs, we confirm one of them goes from 3 lone pairs on the chlorine to 4. We've confirmed the formation of the chloride. The other chlorine goes from 3 lone pairs to 2. Ooh. That means one of chlorine's lone pairs needs to be shared. An arrow has to start from the lone pair and point somewhere else. You guys had noticed that we need to form 2 carbon-chlorine bonds. This pi bond attacking only forms 1. So the lone pair attacking back is what forms the second. Do you have anything you want to add to that, Patrick?
I was going to ask if like when the bonds forms into the electrons for the positive of chlorine or no?
Say that one more time.
So sorry, that came out. Like one of the bonds, if there's an arrow pointing from the bond to the chlorine that's positive to give it one of the electrons, so it has 3 lone pairs.
I don't see any positive charges, though. I'm not sure I'm understanding.
They are in the second half. Yes.
Why doesn't chloride attack chlorine? Why doesn't chloride attack chloronium, actually? Is that what you're saying? Why doesn't the negative attack the positive?
I guess.
Which is a good question. Haven't we been saying everything's just magnets? And that these positive magnets should be drawn to negative magnets? Would you believe me if I said that is partial negative?
Sure.
Because formal charge is different than partial charge. Partial charge is the result of dipole moments from bonds. Carbon to chlorine is polar. So both of these bonds between carbon and the chlorine are polarized towards chlorine. The formal charge is actually just saying that chlorine wants more electrons of its own. It has an octet, but it would like to share less. And believe it or not, chloride attacking this positively charged chlorine will not mean sharing less. It would actually just mean sharing more and expanding its octet.
So like a vacancy sign. A negative charge is like a vacancy sign.
A negative charge is like a vacancy sign? No, I wouldn't say that.
The opposite way?
Oh, you know what? I'm sorry. Yeah, a negative charge is like a no vacancy sign.
Yeah.
Can't
I'm
accept.
saying I'm full.
Yeah. No, but you don't need to think. I don't know that that's helpful. Because it doesn't solve the problem, which is this is going to attack. This is going to use its excess electrons for something. Why is it not attacking this chlorine? It's because that chlorine doesn't want to share more electrons. It wants to share less electrons. How do we get it to share less electrons? Break one of its bonds and give it back. So Yes, this is a positive charge, but maybe more importantly, we should be thinking about the partial positive charge. And the partial positive is at the carbons. And when those partial positives gets attacked, the bond can break back to chlorine and satisfy its positive. Two birds with one stone.
Yeah, that's kind of what I was asking.
Now, how do I know which carbon of this three-membered system my chloride should attack? Well, let's look at the bonds that break and the bonds that don't. The top bond wedged to chlorine doesn't change, but the bottom bond wedged to chlorine does change. It becomes dashed to chlorine. So the bottom bond must be breaking. The top bond is not. And a new bond to the new chlorine is forming at the bottom. So chloride is attacking at this bottom position and breaking that bottom bond open. I've seen students that will try this attacking one carbon, but breaking the bond at the other carbon, which does two things wrong. It expands the octet at one position, and it breaks the octet at the other. So whichever carbon gets attacked needs to lose a bond. Much like what we saw up here. Carbon got attacked, and it lost a bond. Carbon got attacked, and it lost a bond. Substitution.
For the second step, when we draw the arrows, do we have to draw the lone pairs
Nope.
in that situation? We don't, because it has like the negative sign.
You could start from the negative charge. Absolutely.
But the one before,
One,
you have to draw
one,
lone pairs.
one lone pair is relevant.
Okay.
These lone pairs are not changing.
Okay.
These lone pairs are not changing, but one lone pair is being used.
Okay, so you just technically have to draw.
The way that I refer to it is relevant lone pairs.
Okay.
You need to show relevant lone pairs. When is it relevant? If it's changing, if it's being used to form a bond. All right, in our next reaction, we see that the bromine leaves. That's how we're able to get bromide and this positively charged carbon. We see that the oxygen bonds relevant lone pair on the oxygen. There's two lone pairs on the oxygen. One of them is relevant, so make sure you show at least one relevant lone pair. But you guys might see actually from this example, maybe it's too early yet for you guys not to draw lone pairs. Maybe you want to be drawing out lone pairs all the time, all lone pairs. Because being able to assume them doesn't help you. It just helps me, because then I can draw it quicker. So oxygen bonds to carbon by using its lone pair. Okay, let's draw in all the lone pairs and notice how oxygen went from two lone pairs to one lone pair. Nothing happened to the OH bond, which is why that OH bond is still there. And in this last step, bromide acts as our base, deprotonates. A possible mechanism, maybe not even the most plausible, because what might be more plausible is that another molecule of ethanol serves as the base here instead and forms protonated alcohol in the presence of Br-. Where would I get another molecule of ethanol, though? There's only one drawn. Where would another molecule come from? Right, this isn't like a depiction of a battlefield, and this is an account of all of the people present. This is an example of what's happening inside a reaction flask. So we are just pulling out all the fluff and paying attention to what's relevant. But the solvent for this reaction, the reagent that is mediating the reaction, is probably ethanol. This is a solvolysis reaction. So if there's one molecule of ethanol, there's a billion molecules of ethanol. If I've only drawn one, because only one of them is relevant, but if I wanted a second, I would just draw in a second one. That can be a challenge here, because you have to have the freedom to remember there's more molecules surrounding these molecules. All of them are interacting at the same time. This is just a depiction of what change they go through. Oh, there was something yesterday that I wanted to talk about. In the activity that you guys had done, there was this prediction. Early on, one group had predicted that the mechanism that formed an alkene and water in the presence of acid, a reaction that we'll later call acid-catalyzed dehydration. There was a prediction that the mechanism had this intermediate, as opposed to the mechanism having this intermediate first, and then this intermediate. Why would it be wrong to say maybe it happens in 2 steps, maybe it happens in 3? Can't I predict both would happen? Well, I want you to think about how likely all of those changes are. In order for this change in blue to occur in 1 step, you're claiming that at the exact same time, this molecule ran into the acid to form a new OH bond and kicked off a CO bond, all at the same instant. Not that it's impossible, but it does seem like a lot to ask. Now, what if instead this molecule runs into the acid and becomes protonated? Very likely. Not a lot of changing is happening. Then that molecule breaks apart, much more likely. When you ask for a mechanistic step to have a lot of changes happening all at once, it becomes less likely that all of those changes can happen at once. It requires a lot of organization between these molecules to line up and react the way that you're suggesting they might. This was a better route, the one that included that step, because it asked for fewer changes at any given time. Okay. Then on the back side, we had, do you mind if I borrow that again? Thank you. We have this long mechanism, one that involves some resonance. So we started with hydronium, our acid, and a diene, meaning not just an alkene, but 2 alkenes. Can you tell me what role does H3O plus play in this reaction? Is H3O plus a catalyst, a reagent, a product, or both a reagent and a product? That's the definition of a catalyst. So the better answer would be catalyst. I know that was tricky, right? How do you put the definition of catalyst in as one of the options? But we don't say that H3O plus is a reagent because it's not consumed, and that's what happens with reagents. Or I should have said starting material. Starting materials are consumed. It's not a product because products are produced by a reaction. It's not produced, it was there at the beginning. So it's a catalyst. It was there at the start, it was there at the end. It's involved in the mechanism, but it's not consumed by the mechanism. All right, so we saw a protonation step. We see that the pi bond on the right is unchanged, so it's the pi bond on the left that is changing. Does my arrow indicate which carbon is using the pi electrons? No. Can it? Kind of, if I make it all squiggly and kind of draw it through that carbon. But I don't want to see an arrow that points at that carbon and then an arrow from it, because that doesn't really explain how electrons are moving. It's actually better to have it be a little bit more vague. All right, then we see that the pi bond is between carbons 1 and 2 in this reagent. And in the next step, they are not between carbons 1 and 2. And that's because this reagent has resonance. There are 2 resonance forms of this molecule, of this structure, this positively charged structure. So which of them exists? Neither. Or both, depending on how you want to think of it, but I would say neither exists. There's actually a vacancy, a positive charge, on both carbons 1 and 3. The electrons from the nucleophile can be deposited at either carbon 1 or carbon 3. It doesn't matter. And it doesn't have to look like that at any one step. It could attack the resonance form on the right to show how it forms this intermediate, but it can also attack the resonance form on the left, because resonance forms are not different molecules. They're not different structures. So what you do to one resonance form, you could do to any resonance form. So what I want to show you guys is what it would look like forming this next product, whether it attacked the resonance form on the left or whether it attacked the resonance form on the right. It should be easiest for us to say what the arrows look like attacking the resonance form on the right. The lone pair from oxygen is donated to that positively charged carbon. Easy. But to attack the resonance form on the left, there has to be a pi bond change. The pi bond has to move from carbons 1 and 2 over to carbons 2 and 3. And then at the same time, oxygen can donate its lone pair to carbon 1. Both of these separately show the same change. Okay. So resonance means there can be more than one correct solution. One of you may have solved this by first showing the resonance change and then attacking the new resonance form. Some of you may have solved this by showing the resonance movement of electrons and the nucleophilic attack at the same time, which means there are 2 correct mechanisms, 2 correct ways of pushing arrows to show the changes. That's how resonance impacts our mechanisms. And then in this last step, water, the conjugate base of hydronium, acts as a base to reform our catalyst. Okay, questions? Delaney.
Can you draw the bond breaking to the plus, or does that have to be to the opposite?
If you draw it to the plus, that plus is on oxygen, so that would be the same. That would be good. And this can be kind of a challenge about where do you start and end your arrows so that they make the most sense and describe the most appropriately. It is.
Here, John, this is actually.
Tell me if you don't see it.
I'm done.
You did. Okay, good. Alkene nomenclature and reactivity. What I wanted to say, there are times where arrows start in kind of strange places, and it makes it hard for me to figure out what you're saying. For instance, if this deprotonation step had looked more like this, does that arrow start at the hydrogen? It looks like it does. And arrows don't start at atoms. Arrows start at electrons. These are electron arrows, after all. But maybe it was just tight on space, and maybe they were trying to say these electrons are going to the oxygen. So my request to you would be, try to be as clear as possible about where your arrows are starting and ending. Do you guys remember I made like a funny little silly earlier yesterday where I said your arrow can really go anywhere? So if you feel like you're short on space and you can't make that tight U-turn from bond to oxygen, then have it go crazy. It's not that the electrons need to go around the board to make their way over to oxygen. You are just drawing an arrow that explains where the electrons are going. If you've been practicing on active, then you probably have seen that active will just have you click start the electron arrow here and end the electron arrow here, and then it draws it for you in the shortest path possible. There's a reason that you'll be doing mechanisms on your unit test before the final, and that's because active is not the same as putting pen to paper. I don't want you doing a ton of mechanisms on active, thinking it'll just draw itself for me, and then not having an idea of how to do it yourself.
I just want to make sure, on the resonance forms, you did a pi bond to another bond, and that's allowed, right?
Mm-hmm. There's a vacancy at that carbon, so it can accept more electrons. Remember that electrons can be used by atoms, but not really lost by atoms. Well, in the case of the pi electrons, it's owned by two atoms. So if one of them loses it, it's because the other used it. But they can't both lose the electrons, right? One of them can actually lose, but that means the other has to use them. Carbon 2 is the one using them, which is why carbon 2 still has them in the other resonance form. Did I answer your question?
Yeah.
Okay. It's allowed because there's a place for the electrons to go, and because the electrons are still being used, held onto by one of the two carbons that had them originally. More questions on these mechanisms? Okay. Then we're ready to talk about alkenes. Next week, we're going to be doing a lot with alkene reactions, alkene addition reactions. But before we go into reactions with alkenes, I want us to review the structure, the reactivity of alkenes, and nomenclature. We're going to do some nomenclature practice today. So first, let's talk about the molecular orbital depiction of alkenes. An MO diagram, if you recall, has three lanes. On the left-hand lane, we show one of the carbons or one of the atoms in the bond, an sp2 carbon. On the right-hand lane, we show the other atom in the bond, an sp2 carbon. And in the middle lane, we show what bond formations we're depicting. If we have an sp2 carbon, that means that there is 3 orbitals that are sp2 hybridized, and 1 orbital, wrong way, 1 orbital that is unhybridized, atomic p. Why does the p orbital sit higher than the hybridized orbitals? Well, the hybridized orbitals are a mixture of s and p. p orbitals are higher energy than s. So if you hybridize s and p, you're going to get something between the energy of s and p, or in other words, lower than the energy of an unhybridized p. The other sp2 carbon also has an unhybridized p and two sp2s. You don't have all of these orbitals in the diagram I've given you, and that's because these groups are bonding to other things, and they'll need sigma orbitals to bond with them. So we're not looking at all of the possible orbitals. You understand that? These carbons have bonds to other things. We're not looking at those bonds to other things. We're just paying attention to what is going on in this double bonding region. Question, valence bond theory as opposed to molecular orbital theory. Valence bond theory says orbitals overlap to give these bonds. So valence bond theory looks at the carbon-carbon double bond and says 1 sigma from hybridized orbitals overlapping, sp2 to sp2, and 1 pi from unhybridized p orbitals overlapping, p to p. Which of those lines is the sigma bond? Which is the pi? Right. That's a ridiculous question. That's what MO theory does for us. MO theory gives us a depiction of what those bonds actually look like and what energy they have. Which of those bonds is going to break first? Can't say, right? Is it the pi or the sigma that breaks? We can't even distinguish them. That's where MO theory is helping us. All right, these orbitals, I want to look at their shapes. You guys have their shapes on the right-hand side. The sp2 orbital looks kind of like that propeller shape of a p orbital, but usually one of its lobes is larger than the other. When the sp2 orbital overlaps, it overlaps head-on, and it has a significant amount of overlap. Who needs a worksheet did everyone get one? Oh, don't know why I thought somebody came in late. When these overlap well, they have really good constructive overlap, and the energy of their system decreases significantly. And what I get now is the overlap of those two orbitals. Remember that these are just waves. So when waves overlap in phase, they constructively interfere, and they just become one big orbital. It was two different mathematical equations. Now they've combined, and they're one mathematical equation. But if they can overlap constructively, they can also overlap destructively. And if they can be so well stabilized by constructive overlap, then they are equally destabilized by destructive overlap. And notice how the destructive overlap is out of phase with each other. A big unshaded lobe, little shaded, a little shaded lobe, big unshaded. They're out of phase. They're destructively overlapping, and that decreases the energy of the that increases the energy, decreases stability of the mathematical equation.
For the bottom sigma combined bond, should it be darker in the middle and light? Or does it not matter?
It doesn't matter. The reason I gave you guys on the diagram dark in the middle is because you can't see that it's actually just two different shapes overlapped with each other. If I had put white in the middle, you would have seen those rings overlapping. So I did that for the effect of making it look like it's one orbital, one mathematical equation. What's the difference between shaded and unshaded? Their phase, right? Is the wave in the ocean currently pushing up, or is the wave in the ocean dipping down? It's just the phase of the wave, but we don't need to attribute shaded to up or unshaded to down. It doesn't really matter. The idea is that, and I think you'll also see, I showed an sp2 orbital on both sides that have the same shading in the small and large lobes. But then up here, I have a large lobe that's shaded, and I never had that before. So the answer is it doesn't matter whether the little lobe is shaded or unshaded. Both are possibilities, and both are essentially the same, which means you always get the possibility of in phase versus out of phase. You always get both possibilities. When p orbitals overlap, they do not overlap head-on like hybridized orbitals, which means they don't get as much area overlapped. P orbitals overlap side-on, which means the only area that's overlapped is the edges of those lobes. So their constructive interference is less effective. But it also means their destructive interference is less effective. So the molecular orbitals from p orbitals, they actually sit in between the molecular orbitals of the sigma orbitals. In phase combination, out of phase combination. I don't know if you guys know your d orbitals very well. Any chemists in the room will go on to take inorganic chemistry and do a lot with d orbitals. That looks a lot like a d orbital, which is one of the reasons why carbon monoxide and cyanide, which have these pi bonds, can bind so well with iron. It's because they have orbital symmetry with the d orbitals in iron. Now let's talk about where electrons fall. Just because I have the math to describe electrons doesn't mean I'll have electrons to put in there. Okay, each carbon comes with 4 valence electrons. So if I just say each of my orbitals has 4 electrons, each of my orbitals has 1 electron. Remember that 2 of these orbitals are being used to bond to other things. So I'm really just focusing on 2 electrons coming from each carbon. And I decided to put 1 carbon spin up and 1 carbon spin down, because that way when they combine, they'll be paired. Now this is what we're assuming they're starting from, or this is what we already understand about atoms, the orbitals that they have individually. And if those orbitals come together, as MO theory predicts, then all of these electrons will follow Aufbau's principle and fill from the lowest energy to the highest. So first, they'll fill the sigma MO. That's an orbital named sigma, not an orbital named sp2, not an orbital named p, but an orbital named sigma, a mathematical equation formed from the constructive overlap of these orbitals. That was 2 of my 4 electrons. The next lowest energy is for my electrons to fill the pi orbital. That's the name of the orbital. The constructive overlap of 2 p's is called a pi orbital. I ran out of electrons, so I have no electrons occupying pi star, which is an anti-bonding orbital, meaning if electrons did occupy it, it would undo any bonding character that existed. It breaks bonds. I also have no electrons to go into sigma star. Okay. The nature of the pi bond impacts reactivity. That's the first of the blanks. And I want to prove why before I fill in the other blank. The highest occupied molecular orbital. That is the highest energy electrons. Those are the electrons that are going to leave the system if they can. Which of these markers, my blue one or my green one, is more likely to leave their position? It's kind of strange, I know. Maybe not a great analogy. The highest energy is the one at the greatest risk of falling. It's the least stable. If I gave this a little rock, that's got the most potential energy. That's what I want you to think about this as. HOMO, highest occupied molecular orbital. LUMO, not LUMO, sorry, this is actually the LOMO, lowest occupied molecular orbital. And actually it's not, because we're not even paying attention to the 1s orbitals. We're just paying attention to the 2s and 2p. The highest occupied molecular orbitals are pi electrons, which means pi bond breaks before sigma bond. Electrons leave. Does that make sense? If any electrons are going to do something, it's going to be the pi electrons that do something, because they're the highest energy electrons. The LUMO, the lowest unoccupied molecular orbital, the place where I can put new electrons. If I have electrons here and I have electrons here, I can no longer put electrons in these spots. So if I have new electrons to donate, they have to go into the first available place. Wherever the first available place is, that's where electrons will be donated to. Where is the LUMO? Pi star. New electrons added to the system will break the pi bond before they break the sigma bond. Sigma bonds are stronger than pi bonds. It's funny because in general chemistry, there's a common learning objective where we say, what's stronger, a single bond, a double bond, or a triple bond? And you're taught to memorize the trend that triple bonds are strongest, then double bonds, single bonds are the weakest. That's because you're accounting for all of the individual bonds. You're saying a triple bond is strongest because you have to break sigma, pi, and pi. You've got 3 bonds you have to break. In organic chemistry, what I'm asking you to realize is that a double bond is not stronger than a single bond because that's comparing apples to oranges. But a sigma bond is stronger than a pi bond. And MO theory is the one that explains it for us. MO theory says pi electrons start at higher energy, that makes them less stable. And sigma star sits at higher energy, that makes it harder to fill and harder to break. Okay, so the nature of the pi bond means that is the pi electrons are the most reactive, and that the pi bond will break far and away before the sigma bond. The nature of the pi bond impacts its reactivity, how and why it reacts. The nature of the pi bond also impacts its stereochemistry. Okay, and for this, to justify it, let's imagine taking this alkene that I have just labeled. One carbon has two groups, 1 and 2. The other carbon also has two groups, 1 and 2. And I want to rotate around the pi bond. What do we know about this pi bond? We know that it results from the overlap of p orbitals constructively, which means that on one carbon, I have a p orbital in the same phase as the other carbon. If I rotate these two groups, on one of my carbons, you see how before I had 1 and 1 on the same side of the alkene, 2 and 2 on the same side. And just like with our Newman projections from Unit 2, it's like I've rotated around the pi bond, and now I have 1 and 2 and 1 and 2. You guys are okay with this? Taken this pi bond and I've rotated around it. What happens to the p orbitals? They become out of phase. Okay, I kind of screwed up, but no, I'll just redo it then. I didn't really screw up, it just didn't make sense what I had done. Since my carbon on the left has rotated, its p orbital has also rotated. What's that look like? It looks like a d orbital, which we said is the shape of pi star. Because I rotated around that pi bond, I had to physically rotate the p orbitals as well. So my p orbitals are no longer in phase with each other, bonding. My p orbitals are now out of phase with each other, anti-bonding. Congratulations, you've just broken a pi bond. You cannot rotate around a pi bond without breaking it, which means you can't rotate around a pi bond. It's stuck in its bonding constructive overlap configuration. And if you are going to rotate around it, you would need to take those electrons and you'd need to push them into a higher energy orbital, which would be pi star. These electrons have just gone from pi electrons, and as a result of this rotation, they've become pi star. So pi bonds have stereochemistry. Group 1 and 2 cannot switch places. They're locked in whatever configuration they appear to be in. This is a bit of a lie. So a really cool example of breaking a pi bond is when we process fats. This is a trans fat. You guys have heard about trans fats before in nutrition. Trans fats are healthy. Trans fats are produced in nature by plants, by animals. They're actually harder to synthesize in a chemistry lab than their cis version, but trans fats, I'm sorry, I was saying it wrong the whole time. This is a cis fat, and cis fats are healthy. See, there are things you guys are smarter about than me. Cis fats are healthy. Cis fats are produced in nature by plants, by animals. Cis fats are harder to make in a chemistry lab than a trans fat alternative. But this is a cis fat. And if you take cis fats, for instance, harvest some olives, crush them, and then start processing their oils. Any cis fats that were produced by that olive in its oil under high heat and pressure under high heat and pressure, that cis fat becomes a trans fat. And it required high heat and pressure because you had to take those pi electrons and force them to be pi star electrons. You had to break the pi bond in order to rotate around that group. So remember earlier I called this 1 and 1 on the top, 2 and 2 on the bottom, and then we had this relationship of 1 and 2. Here's 1 and 1. 2 hydrogens facing off of the 2 carbons of the alkene in the same direction. And now those 2 hydrogens are facing off of the alkene in opposite directions. Cis fat, trans fat. Trans fats are less healthy. Trans fats are more dangerous on your health. And there's a whole other explanation for that. This has low intermolecular forces with neighboring cis fat molecules. Because of that kink in the carbon chain, molecules can't get close to each other to interact strongly. But after that high heat and pressure breaks the pi bond, lets it rotate, falls down into a trans fat, those molecules don't have a big kink in their chain. Those molecules are just longer, wiggly guys that can get closer to each other, interact more strongly, form solids more quickly, form solids at lower temperatures because they have stronger interactions, and build up plaque in your body. More dangerous, less dangerous on your health, all because of the heat and pressure that we use to process food. The nature of the pi bond impacts both its reactivity and its stereochemistry. All right, before we get into the naming problems that we have down here, let's do a little bit of a review on nomenclature. So, in naming compounds, we have to consider the highest priority functional group first, because we will aim to give the highest priority functional group its lowest locant, and we will aim to put that highest priority functional group into the suffix. In OChem 1, this is not true of all functional groups. In OChem 1, the alcohol is the highest priority functional group. Then the alkene and the alkyne are tied. We're going to talk more about alkynes in the next unit, so I'm not going to spend too much time here talking about how to name alkynes. We're also going to talk about alcohols in the next unit. Then regular alkyl groups and halo groups have the lowest priority. If there's an alkene in the structure, try to get it its lowest locant. Then worry about the locants of everything else. You guys are good with the MO diagram, yeah? The locant for an alkene describes the first carbon of the 2. There's 2 carbons in an alkene by definition, and the locant will always name one of them first. It only describes the first one. Another way of saying this is we count through a carbon-carbon double bond. You can't start your locant on one and then go away from the other carbon. Your locant starts on one of them and numbers through it. For example, this compound is called 1-butene. I don't call it 1,2-butene. I don't describe both carbons of the alkene with a locant. I only describe the first carbon.
It wouldn't be but-1-ene?
Oh, it can be, yes. Yes, it can. Root, locant, suffix. This is what IUPAC is pushing for, but you won't see it all the time. You'll see a lot of places that call it 1-butene. Both are acceptable. I'll take both. If we're in a ring, we do not need to state where the alkene is. We don't need to state its locant, because just like last time, when there's only one group, it's assumed that that's where you're going to start numbering. Methyl cyclohexane doesn't need to be named 1-methyl cyclohexane. Bromocyclopentane doesn't need to be named 1-bromocyclopentane. Cyclohexene doesn't need to be named 1-cyclohexene. We will talk about multiple alkenes. In fact, even if there are other substituents in the ring, we don't have to say where the alkene is, because if the alkene is the highest priority group, of course you're starting at the alkene. How about this? What would we name this compound?
2-methyl cyclohexane.
Why 2-methyl cyclohexane? Okay. And you decided to start at which carbon of the alkene? Right. You could start from either.
1-methyl hexene.
You minimized the locant set for the alkene. You started the alkene at position 1. But you can do that either way. You can call this position 1 of the alkene or this position 1. And what do we do in the case of a tie? Then we move down to the next highest priority group. The alkene can be at position 1 either way. So I'll minimize the locant set for the next priority, the next highest priority. In this case, I don't want to name it 2-methyl cyclohexene because I could name it 1-methyl cyclohexene. And if you wanted to, although you don't have to, you could call this 1-methyl 1-cyclohexene or 1-methyl cyclohex 1-ene. That is implied already because of course you started counting at the first carbon in the chain. All right, now let's change it up a little bit. We can't. We'll always have to specify where the methyl is because the methyl could be on carbon 1. The methyl would never be on carbon 2 if it was just the 1-methyl because being on carbon 2 would be numbering it the wrong way.
So only on alkenes we can share the same locant, or just not even have to say locant number?
We can do that with alcohols as well. Yeah, we'll find next week in lab you guys are doing dehydration of 4-methyl cyclohexanol. and you create 4-methyl cyclohexene. So in both of those cases, we assume the alcohol is at position 1. We assume the alkene starts position 1. Is the best name for this 1-methyl 2-cyclohexene, 2-methyl cyclohexene, or 3-methyl cyclohexene? I have to count through the alkene. It would be nice if I could start here and then just move left. But that does not count through the alkene. Since I have to count through the alkene, my options are to make it 6-methyl cyclohexene or 3-methyl cyclohexene. Once again, I'm just minimizing the locant set for the lower priority group because I prioritize starting with the alkene. 3-methyl cyclohexene. All right, the impact of stereochemistry. First of all, I want to say that we will ignore these labels in rings. And that's because these labels can't really, we're limited to one stereochemical arrangement in a ring. We really can't get both. I'm going to demonstrate that for you. Here is cyclohexene. And this is actually a cis alkene. We're going to talk about how to decide cis and trans, but the highest priority groups are on the same side, kind of like how we had our cis fat over here. If I were to try and draw this as a trans alkene, you see how bad it looks, right? The bond angles don't work. So that's cis versus trans, and the trans version doesn't exist. Can't exist. You can start getting trans alkenes in rings if your ring is bigger than 8 carbons. We're not going to look at those cases. So for the purposes of our class, we don't name cis and trans labels of the alkene inside of rings because for the purposes of our class, our rings will be too small. Oh, something's in the air. To decide whether our alkenes are cis or trans, we're going to follow the Kahn-Ingold prelog rules. First, the rule is a little bit different. First, check to see that both carbons of the alkene have 2 distinct groups. If one carbon has 2 H's, it doesn't qualify. If one carbon has 2 methyls, it doesn't qualify. If one carbon has 2 identical groups, it doesn't qualify for the stereochemistry label. It's not a stereocenter. Instead of assigning 1st through 4th priority, we're going to assign high and low priority. We're going to assign high and low priority to both groups on both carbons. This should feel exactly like what I gave you guys before with the 1, 1, 2, 2. Both carbons have a high and a low priority group. And how do we determine high and low priority? Highest atomic mass at the first point of difference. Highest atomic mass at first point of difference. There are different ways to try and visualize what the conditions need to be, and I'm going to leave that to you on which visualization works the best for you. But some of the ways I've seen students catch on to this. If cis, we also assign the label Z to cis. Z comes from a German word, Zuttengegen or something, and it means same, on the same page, whatever. I actually like to think of it as being the groups will be on the same side. If it's cis, it means that your high priorities both face the same direction, and your low priorities both face the same direction. So in other words, if you bisect the alkene horizontally, you get one side where both high groups are together, one side where both low groups are together. And if trans, the label we give to trans is E, which I actually can't even pretend to remember what it stands for. But I like to say the groups are on opposite sides. Groups are on same side, groups are on opposite sides. It means that your high and low priorities are swapped. Here's what I like to do. I like to take one carbon's high priority and low priority and go from low to high, low to high. If my arrows point different ways, then they're opposite of each other. They're trans. If my arrows from low to high, point the same way, then they're cis as each other. 1-butene. Should we give it a stereo label? Should we call this cis 1-butene or trans 1-butene? Why not? Because it's linear. No, we don't give those labels to rings. But do both carbons have two distinct groups? One carbon has two hydrogens on it. The CH2 of 1-butene disqualifies it from having cis or trans stereochemistry. Because imagine if I swapped the position of those two hydrogens, do I change the stereochemistry? No. Never cis or trans. What about 2-butene? I want you guys to draw the structure of 2-butene. And then see if you run into a limitation on what that name gives you. Do you think that's the best name that it can be? Do you think that really describes the structure that you've drawn in its entirety? You're all pretty much drawing the exact same 2-butene. So did any of you draw this? Is that not 2-butene? It is 2-butene, but it's not what you drew. We put it at the front. This version is Z-2-butene, or we could call it cis-2-butene. Because the high priorities are the carbon groups, the low priorities are the hydrogen, and low to high points the same way on both carbons. Then what do we need to clarify about the structure you all drew to make sure that you draw that structure? E-2-butene or trans-2-butene.
Like the direction of the key is the direction of the carbons, is that what you said?
No, we're saying the relationship of the high and low groups. Would you agree that the hydrogens here are the low priority?
Yeah.
Because carbon is high, so that's low, high, low, high. They face the same direction. The high priorities are facing the same direction. They're cis to each other. Here, low to high priority, those are facing opposite directions, E, trans. Sometimes it's as easy as saying there's a hydrogen and something that's not a hydrogen. But sometimes it's more challenging in that you've got a chlorine on one position that takes high priority and a carbon on the other position that takes high priority. So you might see a kink like this, but that doesn't necessarily mean that it's going to be cis or trans. What I'm trying to say is zig-zig versus zigzag doesn't necessarily predict cis versus trans. Can you name that compound? Anybody want to try?
Z2-chlorobutene.
Oh, close.
2-butene.
2-butene. Or even but-2-ene. Actually, you guys can see that it is a lot more instinctual for me to put the locant of the alkene in front. That's not what IUPAC is asking for anymore, but it is so common, they're going to have to really fight to get that out of there. It's Z because chlorine is high priority and methyl is high priority. Z to each other. Cis to each other, I mean. Zigzag bond line structure, just like the zigzag bond line structure we had here, but this was trans of the high priority groups. The chlorine here made it cis.
Is that so because there's a hydrogen at the bottom of the double bond and a methyl group at the top, so the methyl group is bigger?
Well, carbon is
bigger than
carbon is higher atomic mass than hydrogen.
chlorine is bigger than carbon.
Carbon is higher atomic mass than carbon. Perfect. Chlorine is higher atomic mass than carbon.
So we're looking, the carbon groups we're comparing and looking at are the ones off the alkene.
Correct. Remember when you assigned R and S configuration, you start from the chiral carbon. You don't assign the chiral carbon priority. Here, we're starting at the alkene carbon. We're not assigning it any priority. But you can't start at one alkene without starting at the other alkene carbon as well.
And why do we use the chlorine group and not the other methyl group?
We're using both.
Okay.
Chlorine is a higher atomic mass than carbon,
Okay.
high priority.
Okay.
Carbon is a higher atomic mass than hydrogen, high priority. We have to analyze two groups on two carbons.
So we're just, easy way to do it is just look at the atomic mass based on what's in line with it.
Yep. Find your two carbons, identify those masses. All right, the last thing that I want to talk about here is the multipliers. When we have more than one alkene, we introduce our multipliers. Di for 2, tri for 3, tetra for 4, and then penta and so on for the rest. It's usually the 2, 3, and 4 that you never quite know what you're going to get. Are you going to get di, bi, bis? Are you going to get tri or prop or, yeah, that's the other one, eth? And then we describe the first carbon of all alkenes. So earlier, Elvira was asking about if we have rings, and we have alkenes in the rings, do we need to use our locants there? And the answer is, in general, you should. Yes. In this bottom structure, I have a 5-membered ring with 2 pi bonds. There's only one way that 2 pi bonds can be organized inside of a 5-membered ring. Thank you, Rowan. There's only one way these can be organized. So I don't really need locants because there's no other combination. This compound is referred to as cyclopentadiene. It could be called 1,3-cyclopentadiene, but there is no 1,4-cyclopentadiene. That would just be numbering the wrong way. There is no 1,2-cyclopentadiene. The bond angles won't allow it. But this structure could have a second bond start at position 3. It doesn't. It has a second bond start at position 4. So I would need to distinguish between 1,3-cyclohexadiene and 1,4-cyclohexadiene. And what I have here is 1,4-cyclohexadiene. You want to see something weird about multipliers? Because a multiplier starts with a consonant, and because in general IUPAC doesn't like consonants butting up or vowels butting up, they actually put the A back in. So you notice how we went pent? Pent is for 5, not penta. Pentane, pentene, pentine. But because that multiplier starts with a consonant, they put A back in. Pentadiene, hexadiene. That's the type of nomenclature that if I have you write out a name, I will not grade so harshly on dropping that A or forgetting it. But I do want you to recognize IUPAC, I think, is going by what feels best in the mouth. Cyclopentadiene just doesn't roll quite as well as cyclopentadiene. That, I think, is what they're doing. There is no alkane suffix. That's not what they're doing. They're just putting that A as a spacer. So, wasn't necessary here because there's no other option of where the 2 bonds can go. But there were other ways that the 2 pi bonds could go here, 1,3 or 1,4. So it had to be named to show us which structural isomer we had.
And it doesn't matter which alkene you start at because it'll be 1,4 either way as long as you're following the locant.
As long as you're counting through the alkenes, it'll always be 1,4. Yep. Good. All right, 2 options for us. We can talk about something a little bit different, which will help you make further progress on your homework, or we can use the remaining 15 minutes to do nomenclature practice. First, Sammy.
So like, you know how you can put the 1,4 in front of the ene? Would you put it in front of the diene, or would you put it in front of like hexadi or something, or would you put it in front of
Great question.
just the ene, not the die?
It goes before the multiplier,
Okay.
because I do want to clarify that it's 2 alkenes, diene, and these are their positions, 1,4 diene.
Okay.
Great question. Cyclohexa 1,4 diene. I think I'd rather take you guys away from nomenclature, which we can do more practice on Tuesday, and talk about some other stuff that will help you make more progress on your homework, because I feel like you should be able to make good progress on the nomenclature over the weekend. It's not like it's that much more challenging than it was before.
Yeah, I was doing the active, and it was so confusing. It was giving like
3D models.
yeah, 3D ball and stick models, and it was like what 3 alkenes can make this thing. It doesn't give you the chemical formula.
Right.
It just like tells you what like whites are hydrogens, blacks are carbons.
In fact, we can even talk about that more next week. We can pull up those problems. But to make that question make more sense, I think we should start on the back page. What alkenes can be made? So considering these examples, we want to try and figure out how can we take these molecules and make an alkene? True or false? Making an alkene from these structures true or false, making an alkene from these structures requires an elimination reaction to proceed. True. These structures would need to go through an elimination reaction to make an alkene. I would need to eliminate 2 groups, and from their elimination, be left with a pi bond, a degree of unsaturation. If I eliminate things, it should be less saturated. All of these have what we call a leaving group. A leaving group is usually a halide or this OTS. This is a sulfonate, and sometimes referred to as a pseudohalide. It's actually quite a big organic structure. It has an aromatic ring in it. Sorry, let me just say, this is tosylate. The sulfonate group is that SO3 minus. I'm sorry, my aromatic ring really sucks. And there's a methyl group coming off the aromatic ring opposite the sulfonate. Regardless, you only need to think of this as OTS. It's actually toluene sulfonate, para-toluene sulfonate. We just abbreviate it as OTS. These are what we call leaving groups. They take electrons with them as they leave their carbon atom. And the question is, what alkenes can be made? Well, if these groups leave, that means one group has left 1 carbon, but I'll need another group to leave another carbon in order to have 2 carbons short by 1 group each to make a pi bond. Remember also that we said a pi bond can be described as alpha, beta, 2 carbons needed for the pi bond. So let's call alpha the carbon with the leaving group. with the functional group. Alpha is the carbon of interest. Beta then becomes any carbon adjacent to it. How many carbons adjacent to this alpha carbon? One. Which agrees actually with its degree of substitution. This is a primary alpha carbon, so there should only be one beta position. So if I say my leaving group leaves from alpha, what has to leave from beta in order to make a pi bond? A hydrogen. So we often have a leaving group and a beta hydrogen. These are the two things that leave in order to make an alkene. Rowan, could you grab the door for Jackson? Thank you. I mean, for Jacob. Okay, so what would the alkene look like then? A double bond between alpha and beta, where the halogen has left and a beta hydrogen has left. That is the alkene that we call ethylene. It's our smallest possible alkene. What degree of substitution does my next alpha carbon have? Secondary. So I should be able to find two beta carbons, correct? Here's a beta carbon on the left. Here's a beta carbon on the right. I should be able to show an alkene forming at both beta carbons to alpha. So one version, take the beta hydrogen from the left. The other version, take the beta hydrogen from the right. Do you guys remember that alkene? What do we know about that alkene? No. Not that it has resonance.
It's never cis or trans.
The one on the left is never cis or trans. The one on the right has a stereoisomer. 2-butene could be trans 2-butene, could be cis 2-butene. If I propose that I can make an alkene that has cis or trans stereochemistry, how would I know whether it forms cis or trans? Both of them should be possibilities. What's the degree of substitution at my next alpha carbon?
What does that mean?
Degree of substitution? How many carbons is a carbon bonded to? And this alpha carbon is bonded to 3. All 3 are different, by the way. One is a primary carbon, one is a secondary carbon, one is a tertiary carbon, which means all 3 beta positions are unique.
And we know it's the alpha carbon because it has the most bonds.
No, we know it's the alpha carbon because it has a functional group. Alpha is just the carbon of interest, and usually the carbon of interest is the carbon with a functional group. So I have 3 different beta positions. I should expect to see 3 different alkenes. Can you draw them? Yes.
What are the betas?
Beta comes after alpha. For instance, alphabet.
Okay.
No, that's it. It's just a mapping system.
Oh, I see.
If we assign something as
These are
alpha.
the carbons next to or attached to.
Mhm.
The carbons attached
Yep.
to the alpha carbons.
Because a pi bond has to be adjacent carbons,
Right.
then
Oh, so the beta carbons are the ones that are options for the alkene.
correct. Beta carbons are next to alpha. Those are the only places where a pi bond could form. Great.
Are we saying if the X group leaves? What happens?
Not just the X group. So the X we said in red there is a leaving group. And it actually takes electrons with it. Plus a beta hydrogen is being lost. Like this alkene formed because a hydrogen on the beta carbon was also removed.
No, you're good.
Oh, you lost a couple of You lost a couple of methyl groups. There's 2 methyl groups, 2 methyl groups, 1 methyl group, 1 methyl group. Good start.
Oh, because it's stickier.
That's 2. There's the 3rd. Great. Kayla, you got him. Oh, you lost some methyl group on the far right. Great. That's it. Great work. Redraw the structure. Take off the bromine. Take off a beta hydrogen. Leave a bond in their place. A double bond. That's not done. I'm just drawing a template. We know that all of those carbons are still going to be there. We do. You've added a carbon. 1, 2 methyl groups. Now you have 1, 2, 3. You've also got a 5 bonded carbon, 5 bonded carbon. Remember, the bond to bromine is leaving.
Oh, okay.
Great.
The halogens and
So Gavin, can you walk me through this one? If my alpha carbon loses its bromine and the beta hydrogen on the primary beta carbon, if that leaves,
Isn't that a methyl group?
it is a methyl group.
Isn't it 3 hydrogens?
It has 3. I only need to lose 1. Wasn't this a methyl group?
Yeah.
How many did I lose? I went from CH3 to CH2. If I lose one of my hydrogens here, what will it look like?
Looks like fold down.
A double bond.
Yeah.
Good. It's as simple as that, right? Now, what about if I take a beta hydrogen from the secondary carbon on the left? What does it look like?
Is that where it comes down like this?
Good. Double bond to the left. And then if I take the beta hydrogen from the tertiary carbon
To the right.
to the right. Liana?
Wait, so why couldn't you end up with one that was like, how do you know it's the pi bond is going up on that methyl group rather than down? Oh, because that's not actually, if you had one on the right-hand side, that's not actually attached to the alpha.
So this methyl group over here is not beta. That carbon, that CH3 carbon, is not a beta carbon.
Or what if you put it on the right-hand side of the ring? Like,
If I took this pi bond and drew it there
like here.
instead, so you're asking,
So it's coming off of the beta carbon on the right side, but going down. Inside the ring, yeah.
that is this structure.
Oh, that's true.
But again, identify your alpha wherever the leaving group is, and the pi bond has to form adjacent to that. All right, on the second to last one, how many possible alkenes? Based on our understanding right now, 2 alkenes. You guys might see at the bottom of this page that we're actually going to expect a 3rd alkene later on, once we understand more about alkyl halides and alkenes. And what about the last one? How many alkenes? Why?
The same math. Yeah, too many bonds to carbon.
Rowan said there's 0 because there's no beta hydrogen. There's an alpha carbon and there's only 1 beta carbon. How many beta hydrogens there? 0. It's a quaternary carbon. There are no alkenes that can be made here. Got ya.
Well, I was like, that doesn't work.
Okay, we have more to talk about with alkenes, including degrees of substitution of alkenes. We're going to not use terms like primary, secondary, tertiary, quaternary. We'll use terms like mono, di, tri, and tetra. We're going to talk about how alkenes actually react. And Gavin, you might be able to solve the question, those 3D model questions, but I think after we finish the worksheet on Tuesday, you'll be able to answer it a lot better. Maybe if you can remind me, we can try to answer those in class.
Yeah, so it's due in like tomorrow. Yeah. But it's active, so it doesn't matter.
You want me to push the due date to Tuesday night just so that it stays on your radar?
Yeah, that'd be nice.
Can someone email me about that? I'll try to remember, but if you don't email me, I might not. Thank you guys for your time. Have a good weekend.
Are these all acidic because they're shooting off protons?
That would be the definition, yes. This must be an acid if it's giving away H. It's giving away H+. Which means to form this, we need a base. And whether it's a good base or a weak base, we'll actually talk about that in Unit 5. We're going to talk more about elimination then. Tuesday.
Okay, no worries. Thank you.
You're welcome. I'll send an email, though, this weekend with details on it.
Yeah, I just wanted to make sure it wasn't Thursday because I work all day.
Oh, good.
Wednesday, so I'll come to class Wednesday.
Okay.
But then I leave for like a week.
I'll bring it Wednesday. I'll bring it Wednesday.
Okay, thank you.
Thank you. Oh,